Welcome, friends, I'm happy you're here today. Let's journey back to the universe's dark beginnings when the very first stars ignited and bathed the cosmos, in light shaping everything to come. If you enjoy these calm travels through time, please subscribe or share. Thank you. He sees nothing because there are no eyes yet, and nothing shines because there are no stars yet. But light already fills space as the last scattered glow spreads outward, cooling with the stretch of expansion. After about 380,000 years, the plasma thins into neutrality. Electrons settle onto protons and helium, finishes its earlier steps, so the fog that once trapped photons relaxes, and the cosmos becomes transparent in a quiet way that needs no witness. Hydrogen and helium, almost all of it born minutes after the beginning, now drift as a pale gas across an enlarging geometry. 3 parts hydrogen to 1 part helium by mass, with only a trace of lithium, and the photons that once rattled off free electrons now stream freely, forming a background that will later be called the microwave sky, a map of subtle temperature ripples pressed into it at the moment of decoupling. The fact stands simple, and measured recombination never happens all at once, but unfolds gradually as temperature falls near 3000 Kelvin, and densities decline, and the photon mean free path grows from tiny to cosmic, while baryon acoustic oscillations freeze their pattern into the matter field, leaving compressions and rarefactions as faint guidance for everything that follows. A lesser-known detail lingers in the stillness. Many hydrogen atoms reach the 2's excited state and cannot drop directly to the 1's ground state by a single Lyman alpha photon without being reabsorbed in the thick gas. Instead, 2-photon decay lets them slip past the bottleneck, a slow, rare transition that nonetheless helps the universe complete its quiet turn toward clarity. The neutral gas rests, but not perfectly. A small residual fraction of free electrons remains of order, 1 part in 10,000 to 1 part in 1,000, enough to keep a faint Compton touch with the radiation for a while, enough to leave a signature in the later accounting. In the dark that follows, the cosmic microwave background is everywhere, and yet feels like absence because it is uniform and cold, and without edges to hold the gaze. Transparency arrives and seeing becomes possible, but there is nothing local to see an understated irony that the universe achieves openness before it achieves objects. Another soft irony leans into the mathematics the epoch is named recombination. Though these electrons are binding to these protons for the first time, a tidy linguistic loop that keeps habits of laboratory language in a place without laboratories. A third irony drifts with the gas the moment when photons stop bumping into matter. When light and substance separate their daily business, is also the moment when matter unshackled becomes able to fall more cleanly into the waiting hollows of dark matter. So the age that feels like a pause is also the start of motion with purpose. The new medium is simple, and simplicity governs its cooling. Temperature scales with the expansion, so that as the scale factor grows the gas chills, and with fewer collisions its spin temperature drifts a detail that later allows neutral hydrogen to imprint its hyperfine voice at 21 centimeters against the background glow. The filaments that inflation and gravity have arranged in potential begin as whisper-thin differences in density, but they are enough. Under the invisible weight of dark matter, baryons start to lag, and then to follow a slow permission granted by decoupling. Silence settles. In scales on galactic distances, the brightness drops, while on the horizon of the background the faint pattern endures a precise quilt of microkelvin variations that remembers sound waves in the early plasma and says so without words. Yet a quiet uncertainty persists, and it is honest to leave it resting in the dark. The smallest scales of the primordial pattern are washed away by photon diffusion and pressure before this clarity, so the exact blueprint for the tiniest seeds is not directly seen, and the influence of the supersonic drift between gas and dark matter set at decoupling is still refined in models that test whether early collapse is delayed in some patches more than others. Nothing in this era is hurried, though clocks exist implicitly in half-lives and expansion rates. The cosmic background temperature falls as one divided by the scale factor, while densities fall as one divided by the cube, and the collision rates that tie matter and radiation fade accordingly step by measured step. The universe does not repeat itself here, but it rhymes. Helium has its own recombination sequence earlier than hydrogen, and in both cases transparency is not a switch, but a thinning of obstacles, as if fog does not lift, but opens to an ever longer view. The chemistry is not busy because there are so few ways to combine when only the first elements are present, yet a few paths already prepare tomorrow's work. Residual electrons and trace ions allow the first faint molecules to form especially molecular hydrogen by channels that use intermediaries like negative hydrogen or molecular hydrogen ions, but those will matter more later when the dark deepens enough for cooling to require them. For now, the significance is simpler. Photons no longer share energy rapidly with the gas, so matter begins to cool faster than radiation, and the two temperatures slip past each other a small divergence that will become a history of structure. The background glow keeps its perfect spectrum as it shifts toward longer wavelengths, a black body stretched without distortion, and that perfection is itself a gentle comparison. A bell that rings across time without losing tone, while the matter underneath forgets the sound but follows the pattern left by its pressure. In a present tense that holds for hundreds of millions of years, neutral hydrogen and helium drift as a nearly uniform sea, changing only by expansion and by the slow accrual of influence from slight over-densities. Nothing burns, nothing shines, but gravity already rehearses the first steps of gathering. This scene remains austere, a room emptied after a crowded meeting with chalk dust still in the light, except that the chalk dust is the background and the room is space itself, and even this analogy is too warm for the reality of a 13-billion-year-old quiet. The truth that matters is straightforward and patient. Once the fog clears, every later light will be free to travel, every later explosion will be able to announce itself, and every later atom of carbon will someday inhabit a lattice or a cell, because the universe, in becoming neutral and transparent, grants passage to information. It is a beginning that looks like an ending, the turning off of scattering, that allows the turning on of memory, and it is a darkness that already contains its future morning, not by promise, but by physics like dawn seeping through fog that is not weather but equation. The neutral gas drifts its temperature sinking with the slow expansion, the background glow receding into wavelengths too long for any structure to reflect, and the cosmos moves into what will later be called the Dark Ages, a name that is both precise and misleading. For while there is no starlight or galaxy, the microwave background still suffuses all space, invisible now to any eye that could exist. A low hum without variance to break the uniformity. Hydrogen atoms with their single electrons bound to single protons and helium atoms, mostly in the form of helium-4, fill the expanding void with an almost perfect regularity, interrupted only by the faint ripples left over from earlier acoustic motions. The fact that dominates this era is that the gas is adiabatically cooling faster than the radiation field, for with no free electrons to scatter photons efficiently, the matter temperature drops as one divided by the square of the scale factor, while the radiation temperature drops only as one divided by the scale factor itself, a steady divergence that will later allow the gas to become cold enough for gravitational collapse when the right densities form. A quieter, more intricate detail threads through the emptiness, the hyperfine transition of neutral hydrogen. The flip of the electron spin relative to the protons exists as a tiny energy difference. and though its photons are scarce, they carry a frequency that will one day become a tracer for the density and motion of this gas through the long night. Yet the signal lies dormant for now, its spin temperature coupled to the radiation field, offering no contrast to the background until other processes stir it from equilibrium. There is a soft irony in this interval. The universe has finally become transparent, and yet in human terms there is less to see than before, as the last brilliant scattering has faded, and nothing luminous has yet taken its place. Another irony rests in the idea that while gravity is already shaping the gas, the forces doing the most work remain entirely invisible, their mass locked in non-baryonic particles that neither emit nor absorb light, shaping everything without ever showing themselves. A third irony drifts in the numbers. The matter filling the universe now is mostly hydrogen and helium, yet these simple atoms will later be assembled into the most intricate structures, known from molecular clouds to living cells, and here at this early time their behavior is governed only by temperature and gravity. The cosmic web begins to sharpen its filaments defined by slight over-densities, where dark matter is denser, and baryons slowed by residual thermal motion begin to pool. The gas feels a weak pull toward these filaments while voids grow emptier, as expansion carries them farther from the regions where matter gathers. The uncertainties here are not about whether collapse will happen, but about how small the earlier structures can be for the relative streaming velocity between dark matter and baryons. Set at the time of recombination, may slow the condensation of gas into the tiniest halos, delaying the moment of first light by a margin still measured in models. Cooling continues without drama. Without metals or dust, the only viable pathway for the gas to lose its heat efficiently is through the rotational and vibrational transitions of molecular hydrogen, and this molecule is rare in the beginning, formed through slow gas phase reactions that require the presence of trace ions and electrons left over from the earlier epoch. Over tens of millions of years, these molecules accumulate in the densest knots of the cosmic web, but they remain too sparse to affect most of the gas which floats untouched in the expanding medium. The background temperature falls below 100 Kelvin, then below 10. But the darkness is absolute, not because the photons are gone, but because they are all of nearly identical energy and direction, too uniform to pick out any difference between one point in space and another. The vast stillness is broken only in thought for nothing. Here moves quickly relative to the horizon scale, and yet the seeds of collapse deepen in silence. The hydrogen atoms that dominate the universe are simple, but their simplicity is deceptive. Their resonance lines their scattering cross-sections. Their ionization thresholds are the scaffolding on which the future interplay of radiation and matter will hang. At this stage, they merely drift cold and neutral, but each is a reservoir of potential energy, a collection of bound states waiting for a photon of sufficient energy to free it. The darkness is not static, for the curvature of the gravitational potential in the filaments continues to pull more gas inward, though the timescales are long set by the low densities and the gentle gradients. Slowly, over tens of millions of years, these flows will increase the central density of the small halos until conditions allow collapse, but for now the process is imperceptible. It is a strange interval in cosmic history. Expansion dominates, cooling dominates, but formation of luminous objects has not yet begun, so the universe appears quiescent while it prepares its first transformation. The 21-centimeter line, already part of the atomic structure, remains unexpressed as a map of contrast. And this is another quiet irony, that the most informative tracer of the Dark Ages exists in principle, but cannot yet be seen in practice, awaiting the change in spin temperature that will come only when the gas decouples thermally from the background radiation. The interplay of scales is gentle and precise. The Jeans mass, which marks the smallest clump of gas that can overcome its own pressure to collapse under gravity, slowly falls as the gas cools, opening the way for smaller structures to form. The first halos with masses of around 100,000 to 1 million times that of the Sun will be the ones to gather enough molecular hydrogen for cooling to proceed rapidly enough to ignite star formation. But until their central densities rise above the threshold, they remain invisible in every wavelength. In the background, the cosmic microwave radiation continues its perfect expansion, its temperature now only a few tens of Kelvin, yet still shaping the chemical balance of the gas through rare interactions. This period lasts for over 100 million years, a span that in human terms would seem beyond measure, yet in cosmic terms is only the briefest pause between the last scattering and the first ignition. The absence of light is not the absence of change, but change here is measured in the slow accumulation of conditions rather than in events. Every hydrogen atom in the universe now is older than any future star, and every photon in the background has travelled farther than any future galaxy will span, yet the stage is still bare, a set built from invisibility. Gravity is the only active artist bending the paths of matter toward convergence, and the script it follows is written in the fluctuations set down in the earliest instants. In the darkness, the universe is already leaning toward its first sunrise, a sunrise that will not break over any horizon, but will seep into the void as light begins to spread from scattered points, dissolving the last of this uniformity. For now, the sea of hydrogen and helium drifts without interruption, holding its energy in the quiet cold, waiting for the first dense cores to cross the line from silence to light. The darkness holds, but not evenly. Across the immeasurable volume of space, slight ripples in density begin to press their advantage, their extra mass bending the flow of matter ever so slightly toward them, and with each passing million years the contrast deepens. These are the filaments of the cosmic web drawn out by gravity from the faint blueprint left in the first fraction of a second, and now becoming the scaffolding for all to come. Within them, dark matter leads collapsing first into bound halos whose depths are invisible yet real, their shapes determined only by the pull of their own gravity and the absence of any radiative loss to slow them further. The baryonic gas made only of hydrogen, helium, and trace lithium feels the same pull but resists with thermal motion, its atoms colliding and pushing outward even as gravity draws them in. The fact that guides the next step is clear. For collapse to proceed efficiently, the gas must shed its heat, and with no metals or dust to act as radiators, the only available coolant is molecular hydrogen, rare, but forming in sufficient amounts in the densest knots. The process of its formation is delicate and slow, relying on the few free electrons left from recombination. A hydrogen atom can capture an electron to form negative hydrogen, which can then combine with another atom to make molecular hydrogen, or alternatively two atoms can pass through an intermediate molecular ion before arriving at the same result. The rate is low, but over tens of millions of years these molecules become the difference between stasis and collapse. A lesser-known detail hides in the geometry of the forming structures the first potential wells to trap gas deeply enough to allow cooling are not the largest, but the ones with masses around 100,000 to 1 million solar masses, for in these the densities and velocities balance to make molecular hydrogen both stable enough to survive and abundant enough to radiate away heat. Within these halos, gas begins to sink toward the center, compressing and heating, and here the ironies multiply. The first is that in order to create light, the gas must first fall into darkness, gathering in regions where no light yet exists, and losing its energy invisibly. The second is that while the dark matter halos are the true architects of structure, they will remain forever unseen, revealed only by the light of the baryons that follow their shape. The third is that although these halos are small compared to the galaxies they will one day merge into, they carry the seeds of nearly everything that will later dominate the visible universe. The quiet uncertainty here is about timing and abundance, How many of these early halos form quickly enough to ignite stars before feedback from the first light sources halts the process, and how their distribution shapes the topology of the earliest illumination. As collapse proceeds in the most favourable halos, molecular hydrogen cooling allows the central gas to drop below a few hundred Kelvin, enough to lower the gene's mass and accelerate the infall. The density increases by orders of magnitude, forming a core that is still enormous compared to any future star, but that is destined to fragment or continue contracting into the first stellar object. The surrounding gas, still part of the halo but too diffuse to collapse, yet waits for either further cooling or external compression from future shocks. Across the web, the pattern repeats, though only in the rare peaks of the density field, while the majority of space remains an almost perfect vacuum, expanding and cooling toward irrelevance. The gas falling into halos is not uniform in composition, but the differences are minute. There are no heavy elements to alter cooling pathways and no dust grains to shield or scatter light, so the physics is pure in a way that will never again be repeated. The mass infall rate depends on the depth of the potential well and the surrounding environment, and in some cases the flows along filaments feed halos steadily, while in others the supply is limited by the expansion of the voids around them. This is a time without turbulence on the scales familiar to later galaxies. The flows are smooth, and the boundaries between void and filament are wide, defined by gradients in density rather than by shocks. The background microwave glow continues to fade in temperature, its perfection intact, its pattern still faintly mapping the origins of these filaments, but its energy is now too low to interfere with the cooling of molecular hydrogen in the densest cores. The halos that have not yet reached the threshold for collapse continue to accrete dark matter, and baryons, slowly their central densities rising on timescales of tens of millions of years. But for those that do reach the threshold, the transformation from near-static gas to a contracting protostellar core begins almost abruptly, yet even here the process is far from instantaneous. Freefall times in these environments are long, and the conversion from cloud to star takes hundreds of thousands of years, during which the gas must continue to radiate away the heat of compression. The most important irony in this stage is that the first step toward creating light is defined by loss, the loss of thermal energy to invisible photons of molecular hydrogen, carrying away the very heat generated by gravitational compression. Another is that while gravity drives the collapse, it is cooling that decides its success, a partnership between attraction and dissipation that will govern star formation for all time. A third is that in these pristine clouds there is nothing yet to block radiation, so the cooling is as efficient as the available channels allow, even though those channels are few. The uncertainties here remain even in the most refined models. Whether the gas fragments into multiple cores or remains as a single massive object is determined by the precise balance of cooling and accretion, and without direct observation the outcome can only be inferred from theory and from the chemical signatures left in later generations of stars. In the broader view, the cosmic web is still mostly dark, with only a tiny fraction of space engaged in this first act of star formation. Yet these rare locations will soon change everything. As gas continues to flow inward along the filaments, the deepest halos grow denser, and in their cores the first seeds of starlight gather mass in silence. The scene remains austere cold hydrogen, rare helium, sparse molecules, invisible dark matter, all working without colour or sound, toward a threshold beyond which the universe will never again be the same. In the absence of light there is no shadow, and so the progress here is without visual marker, but the physics is precise, inevitable, and without pause. Over the next few tens of millions of years, these collapsing cores will reach temperatures and densities high enough for nuclear fusion to ignite, and when it does, the darkness will be pierced for the first time since the cooling of the background glow. For now, the gas continues to sink, the molecules continue to radiate, and gravity continues to draw matter together into knots that will become the first stars, though nothing yet betrays their presence. In the densest knots of the cosmic web inside the protective hollows of dark matter mini-halos, the collapse deepens and the gas that has been falling inward for millions of years begins to gather in the center with a speed that no longer matches the slow pace of the surrounding universe. Molecular hydrogen continues its quiet work as the only coolant allowing the temperature of the gas to fall to a few hundred Kelvin despite the growing density. This is the fact that underlies the moment. Without the rare molecules, the collapse would stall, pressure would balance gravity, and the dark ages would stretch on unbroken. The gas now forms a roughly spherical cloud within the core of the halo tens of light years across, with densities millions of times higher than the average of the intergalactic medium, and in its innermost region a single dominant clump begins to take shape. The lesser-known detail here is that cooling by molecular hydrogen is not uniform. Its efficiency depends on both the density and the temperature, and once the density becomes high enough, the cooling rate no longer increases in proportion, leading to a phase where the gas contracts nearly adiabatically, storing more of its compressional heat. This transition marks the beginning of the protostellar stage. The first irony lies in the way the universe's earlier structures must fight their own heat, as though the very act of assembling resists completion. The second is that the gas collapses toward forming an object that will soon burn brightly enough to unmake the very environment that formed it. The third is that in a universe almost entirely composed of hydrogen and helium, the most important events are now happening in regions where the amount of gas is minuscule compared to the cosmic total, yet their effects will spread far beyond their birthplace. The quiet uncertainty that threads through this stage is how much fragmentation occurs before ignition. Simulations suggest the first stars could form in isolation as enormous single bodies, or in small multiples depending on the interplay of turbulence, cooling, and angular momentum, but the lack of observation leaves the outcome unsettled. The collapsing core spins slowly, and as it contracts, the rotation increases, flattening the gas into a small, dense disk around the central condensation. From this disk, material continues to feed the growing protostar, spiraling inward and releasing gravitational energy as heat and low-level radiation that cannot yet escape to any distant observer. Infalling gas from the larger cloud continues to replenish the disk, and shocks within it heat the gas locally, though the overall temperature remains low enough to prevent immediate dispersal. The background universe outside the halo is still cold and dark, and the isolation of this process is complete. There are no nearby stars to heat the gas, no external ionizing photons to strip it, and no metals to enhance cooling or change the chemistry. The freefall timescale at the densities now reached in the central regions is on the order of 100,000 years short in cosmic terms, but long enough for the structure to evolve through several distinct phases before nuclear fusion begins. At the center, the density becomes so high that the gas is optically thick to its own molecular hydrogen radiation, and cooling slows dramatically. The temperature begins to climb first to hundreds and then to thousands of Kelvin, and the hydrogen molecules themselves begin to dissociate, absorbing energy in the process and providing a temporary buffer against further temperature rise. This dissociation is the final cooling stage before the core becomes dominated by atomic hydrogen, and once it is complete, the temperature climbs rapidly toward the threshold for nuclear fusion. The mass of the forming star is already far greater than that of most stars that will exist in later epochs. Without metals to enable efficient cooling and fragmentation, the infall rates are high, and the core can accumulate tens to hundreds of solar masses before radiation pressure begins to oppose accretion. This tendency toward massive stars is a simple result of the physics of primordial gas, but it will have profound consequences for such stars burn quickly and die violently, scattering the first heavy elements into space. The environment around the forming star remains dark, for even as the central object contracts and heats, its earliest light is trapped within the thick gas surrounding it, absorbed and re-emitted at longer wavelengths that cannot escape the halo. From outside, nothing would yet be visible, not even the faintest glow, though inside the halo the temperature is beginning to rise, and the chemistry is already changing as molecular hydrogen is destroyed near the forming star. The first irony of this moment is that light exists before it can be seen, confined to the cocoon that will soon be destroyed by its own source. The second is that the star, once it emerges, will live only a fraction of the time it took to form, burning through its fuel at a rate that will leave no long-lived remnant. The third is that this enormous investment of gas into a single star will be repeated across many halos, each isolated from the others by millions of light years, yet all unfolding the same process in parallel. The quiet uncertainty here is in the exact mass distribution of these first stars, for while theory favours the most massive, even a small fraction of lower mass survivors would carry the pristine chemical signature of the early universe, but none have yet been found. The final stage of collapse is swift. The central temperature rises to the point where hydrogen nuclei begin to fuse into helium through the proton-proton chain, and the CNO cycle, though the latter requires trace amounts of heavier elements, and so is absent here. Fusion releases enough energy to counterbalance gravity, and the star settles into a short but stable main sequence life. The gas around it is instantly transformed, for its ultraviolet photons ionize the surrounding hydrogen, creating a sharp-edged bubble of ionized gas that expands outward at supersonic speeds. The ultraviolet radiation also destroys molecular hydrogen in the surrounding halo, halting further cooling and delaying new star formation nearby. The birth of the first star is thus also the birth of the first stellar feedback, the earliest instance of light reshaping the medium from which it came. This is the fact that closes the stage with ignition. The dark ages begin to end not everywhere at once, but in scattered, expanding regions of light. The lesser-known detail is that the very first ionizing photons must fight against the dense gas still close to the star, so the earliest expansion of the ionized region is slow until the local density falls enough for the front to accelerate. Beyond the halo, the universe remains unchanged for now, its vast stretches of hydrogen still cold and neutral, but the first points of light have been kindled, and they will multiply. The scene is still overwhelmingly dark, the light from the first star invisible beyond its own small bubble, but the balance has shifted. The cosmos is no longer entirely without stars, and the long night has begun to break in scattered places. The first stars burn with a brilliance that would overwhelm any eye, though none exist to see them, their surfaces reaching tens of thousands of Kelvin and pouring out ultraviolet photons in numbers that dwarf anything that will come later on a per-star basis. Their light moves outward into the surrounding halo, ionizing hydrogen and helium, heating the gas to tens of thousands of Kelvin and driving an expanding front of ionization into the cold medium. The fact that defines this stage is that these earlier stars, the population 3 generation, are metal-free and extremely massive, often exceeding several tens or even hundreds of times the mass of the Sun, and their nuclear reactions proceed at extreme rates, leading to lifespans of only a few million years before their cores collapse or explode. The lesser-known detail is that their spectra, dominated by intense ultraviolet emission, include strong Lyman alpha lines that can scatter through the surrounding gas, coupling the spin temperature of neutral hydrogen to the kinetic temperature of the gas, and allowing the 21 centimeter line to emerge in absorption against the background radiation for the first time in cosmic history. This transition, though subtle, is the opening of a new observational window into the early universe, The first irony here is that the same radiation that reveals the gas also begins to erase it in its neutral form, turning the very medium that carries the signal into something transparent and silent. The second is that these stars, though the first to bring light to the cosmos, will be gone in an instant compared to the dark ages that preceded them. The third is that their creation of heavier elements, the very materials that will later allow planets and life, comes at the cost of destroying their own pristine simplicity. The quiet uncertainty rests on their exact mass distribution and rotation rates, as these determine whether they die as pair instability supernovae, core collapse supernova, or directly collapse into black holes without explosion. Around each star, the ionized region grows first slowly within the dense halo, and then more rapidly once it breaks into lower density surroundings. The heating of the gas drives it outward, reducing the density near the star and limiting the rate at which new material can accrete. In some halos, this process effectively ends further star formation, until the gas can cool and fall back, which may take tens of millions of years. In others, if multiple stars form nearly simultaneously, their ionized regions merge quickly, creating a larger bubble of hot plasma in the intergalactic medium. The feedback is not only radiative. Strong stellar winds carry momentum into the surrounding gas, further dispersing it and mixing it with the first traces of heavier elements. The scale of these effects is small compared to the entire universe, yet locally they are transformative, turning cold, neutral hydrogen into ionized plasma and pushing it outward into the cosmic web. The light from these stars travels far beyond their own halos, but space between halos remains neutral, so the radiation is gradually absorbed, particularly at specific resonant wavelengths, creating a complex pattern of illumination and shadow on cosmological scales. Over time, more halos cross the threshold for star formation, and the number of light sources grows. In regions where halos are clustered, their ionized bubbles can overlap quickly, creating irregular patches of reionized space, while distant voids remain untouched. The lesser-known physical process at play here is the role of Lyman-Werner photons with energies just below the hydrogen ionization threshold, which can dissociate molecular hydrogen in nearby halos and delay their cooling, thus regulating the timing of subsequent star formation in their vicinity. This effect, subtle yet far-reaching, ensures that the growth of light across the universe is not smooth, but staggered with bright regions suppressing their own expansion indirectly by slowing the ignition of new stars nearby. The first irony in this is that the most luminous objects of their time are also the most effective at halting the rise of their own kind. The second is that the earliest networks of light emerge not from cooperation but from the random clustering of rare halos in the density field. The third is that while the light travels freely through ionized regions, it cannot yet cross the neutral voids without being absorbed, so the universe is still mostly dark to distant observers. The uncertainty here lies in how rapidly the overall ionized fraction of the universe grows. Models suggest it depends strongly on the star formation efficiency in the smallest halos and on the relative contribution of early black holes, but direct measurements from this epoch are sparse. Inside each ionized bubble, the temperature of the gas remains high enough to prevent immediate recombination, but at the outer edges the ionization front slows and sharpens, balance between the incoming photons and the recombination rate of the partially ionized gas. Beyond this thin shell, the gas remains cold and neutral, largely unaffected by the existence of the star at its center. In the last phases of their lives, the most massive stars exhaust their nuclear fuel, their cores contracting under gravity until instability takes hold. Some explode with extraordinary violence, pair instability supernovae, releasing enough energy to unbind the entire star and scatter heavy elements into the surrounding gas without leaving a remnant. Others collapse to black holes swallowing their own cores, and possibly powering short-lived but intense bursts of high-energy radiation. The metals dispersed by these explosions, carbon, oxygen, silicon and others, mix slowly with the surrounding gas, changing its cooling properties forever, and enabling the formation of lower-mass stars in the future. This is the closing fact of the stage. The death of the first stars marks the chemical end of the pristine universe, setting the stage for all subsequent cosmic history. A lesser-known detail is that the energy from the explosions can drive shocks far beyond the original halo-compressing gas in some places, and triggering collapse while sweeping it away in others. In this way, the first supernovae act both as destroyers and as catalysts, a duality that will repeat in every later generation of star formation. The first irony here is that the stars that end the darkness also ensure that the darkness will never return in its original form, for their light and debris permanently alter the medium. The second is that their most enduring legacy, the metals they create, are invisible to them, for they do not survive to see any structure that uses them. The third is that in a universe just beginning to shine, its brightest lights are already fading. The uncertainty that lingers is the balance between the stars that collapse quietly into black holes and those that explode, a ratio that determines how quickly the universe becomes enriched with heavy elements. As more halos form stars, the process of reionization accelerates, though it remains highly inhomogeneous, with bright clusters of overlapping bubbles separated by vast stretches of neutral gas. In the global view, the dark ages are ending, but to any point in space not yet reached by starlight, the silence remains. The transformation is not a single event, but a gradual knitting together of illuminated regions, a slow dissolution of the neutral intergalactic medium into a fully ionized expanse. For now, each first-generation star is a singular beacon in a still dominant night, its light both a promise and a warning of the changes to come. The light of the first stars, though brilliant, does not travel unopposed. Every ultraviolet photon that leaves an ionized bubble eventually meets neutral hydrogen somewhere in the vast intergalactic medium, and there it is absorbed, vanishing into heat, or re-emitted in a cascade of lower energy photons. The regions between early clusters of halos remain deep in shadow, filled with cold hydrogen and helium, their temperatures still only a few degrees above absolute zero. The fact that frames this stage is that the early universe's illumination is patchy and uneven, determined by the rare peaks of the primordial density field, where mini-halos formed first, while most of space remains untouched by starlight. This patchwork produces a cosmic landscape, where reionized bubbles expand into the darkness at different rates, depending on how many sources lie within them. A lesser-known detail in this early expansion is the subtle redshifting of Lyman alpha photons as they scatter through the neutral intergalactic medium, creating a diffuse background that can couple the spin temperature of hydrogen to its kinetic temperature over immense distances, preparing the gas for detection in either absorption or emission against the cosmic microwave background. The first irony here is that this resonant radiation, though able to affect hydrogen across the universe, leaves no visible glow in the human sense, for its wavelengths are too short to survive travel through the remaining neutral gas without being scattered out of view. The second is that even as the first stars strive to extend their reach, the growth of ionized regions is constrained by the limited number of sources and the rapid recombination in denser areas. The third is that in a universe dominated by gravity, the reach of light is determined more by the geometry of matter than by the intrinsic power of its sources. The quiet uncertainty here is the exact size distribution of the early ionized bubbles, for while simulations suggest typical scales of a few million light-years at this stage, direct observation remains beyond current capabilities, leaving only indirect traces to guide inference. Inside the bubbles, the heating of the gas changes the future evolution of structure. With temperatures of 10 to 20,000 Kelvin, the gene's mass rises, making it harder for smaller halos to accrete and retain gas. This photoheating feedback ensures that subsequent star formation becomes biased toward larger halos that can resist evaporation of their baryons. At the same time, Lyman-Werner radiation from the first stars continues to permeate the surrounding regions, dissociating molecular hydrogen and preventing cooling in nearby halos that might otherwise have formed their own stars. These dual feedback mechanisms, heating and molecular dissociation, create a staggered self-regulating growth of the luminous population. Beyond the reach of any ionized bubble, the cold gas remains bound to the cosmic web, slowly accreting into halos that have yet to cross the cooling threshold. Here the neutral hydrogen is undisturbed, preserving the pristine conditions of the post-recombination universe. The lesser-known chemical processes of this untouched gas include the slow formation of trace molecules like HD-deuterated hydrogen, which, though rare, can cool gas to even lower temperatures than molecular hydrogen if present in sufficient abundance. Yet in most regions, these molecules remain too scarce to change the collapse threshold significantly, and the gas continues its slow drift toward the nodes of the web. The first irony in this untouched darkness is that it holds the same raw materials as the brightening regions, yet it will form its first stars much later, simply because it lies farther from the early peaks. The second is that its stillness is not stability, for gravity is already shaping its fate even in the absence of light. The third is that in this shadowed majority of the universe, the ancient microwave background is still the only pervasive illumination and memory rather than a present act. In the overlapping fringes of growing bubbles, new phenomena emerge when two ionized regions meet. The boundary between them vanishes almost instantly, and the combined volume allows light to travel farther before absorption, accelerating the progress of reionization in that locale. The rate at which this patchwork merges depends heavily on clustering in dense regions. Many halos contribute, while in sparse areas a single source may remain isolated for millions of years. The uncertainty that persists here concerns the contribution of the first black holes to this process. Some massive population 3 stars collapse directly to black holes without a supernova, and if they accrete gas, they can emit copious X-rays capable of penetrating neutral hydrogen over much larger distances than ultraviolet photons. Such X-ray heating could raise the temperature of the intergalactic medium in advance of reionization, altering the observable 21 centimeter signal, but the extent and timing of this effect are not yet precisely known. Within the bubbles themselves, the radiation field is not uniform. Close to the stars, the gas is fully ionized and hot, but toward the edges, partial ionization and recombination create complex layers of varying temperature and ionization state. The Lyman alpha photons emitted here can scatter many times before escaping, creating a diffuse glow that would be visible to a suitably placed detector, but that cannot be directly observed from Earth until much later in cosmic history. The energy deposited into the intergalactic medium by the first stars also influences its chemical state, ionizing helium, once in places where the photons are energetic enough, though full double ionization of helium will wait for the arrival of more energetic sources in later epochs. The larger scale picture is one of slow but inevitable change. More halos form, stars, more bubbles grow and merge, and the volume of ionized gas increases from a negligible fraction toward eventual dominance. The process is not smooth. Bursts of star formation in clustered halos can produce sudden local expansions of ionized volume, while the death of massive stars can temporarily slow the growth if no new sources take their place immediately. The first irony in this is that the overall march toward reionization can be driven as much by the statistical clustering of halos as by the properties of the stars themselves. The second is that the recombination of hydrogen within already ionized regions constantly works against progress, requiring a steady supply of new photons to maintain the state achieved. The third is that even after a bubble has expanded its internal density, fluctuations can create pockets of neutral gas that survive for millions of years hiding in the brightened landscape. The quiet uncertainty that lingers is about the exact timing of when the global ionized fraction reaches 1/2 a milestone that marks the midpoint of reionization, but that is difficult to measure directly. It depends on the balance between the birth of new sources, the death of old ones, and the complex recombination rates in an inhomogeneous medium. As the universe moves through this stage, the visual appearance would be that of a cosmic archipelago, luminous islands of ionized gas glowing around the first stars and star clusters set in a dark ocean of neutral hydrogen. The scale of the islands grows, the ocean shrinks, and yet for a long time most of the cosmic volume remains unlit. In the deepest voids, the darkness is total, broken only by the uniform ancient glow of the microwave background, now cooled to a temperature barely above absolute zero. The forward motion of reionization is inevitable, driven by the increasing number of sources and the merging of bubbles, but it will take hundreds of millions of years to complete, and the darkness will retreat unevenly, holding out longest in the largest underdensities. For now, the universe is a mosaic of night and dawn, with the balance still tilted toward the night, and every new star that forms is a point of light in the slow unraveling of the dark ages. The first supernovae erupt into the young universe with an energy release that sweeps through their host halos and into the surrounding medium, driving shock waves that heat compress and enrich the gas with the earliest heavy elements. These explosions are brief in duration, yet immense in consequence, each one capable of expelling most of the baryonic matter from a small halo, leaving it devoid of the raw material needed for further star formation until the gas can cool and fall back. The fact at the center of this stage is that such feedback marks the beginning of chemical evolution, ending the primordial composition of hydrogen, helium, and trace lithium, and introducing elements like carbon, oxygen, silicon, and iron into the cosmic inventory. These atoms, though vanishingly rare compared to hydrogen, change everything. They provide new cooling pathways through fine structure lines, and allow gas to fragment into much smaller clumps, making it possible for lower mass stars to form in the next generations. A lesser known detail lies in the reach of these metals. Simulations show that in low-density regions around mini-halos, the ejecta from a pair instability supernova can travel hundreds of parsecs before slowing enough to mix with the ambient medium, creating isolated pockets of enriched gas far from any ongoing star formation. The first irony here is that the most violent stellar deaths also act as the first fertilizer for future creation. The second is that in scattering their substance so widely, these stars ensure their own kind will become rarer, for once the gas is enriched, the same processes that made them massive will be replaced by cooling channels that favor smaller stars. The third is that this enrichment, essential for everything that follows, occurs without any witness or record beyond the altered chemistry of clouds yet to form. The quiet uncertainty is in the completeness of mixing. If metals remain unevenly distributed, some regions may continue forming population 3 stars long after others have shifted to lower mass populations. The supernova shock waves do more than enrich. They also compress surrounding gas, and in some cases this triggers star formation earlier than it might have occurred otherwise. In dense filaments feeding the halos, the shocks can pile gas into knots that cool, rapidly collapsing into the first metal-enriched stellar clusters. Yet the same blast can also sweep away gas from smaller halos, halting star formation entirely in those locations for tens of millions of years. In clustered regions, overlapping supernova remnants create a turbulent, heated intergalactic medium, expanding the influence of early feedback beyond the boundaries of any single halo. This turbulence mixes metals more efficiently in these regions, while in more isolated halos the enrichment may remain confined and localized. The interplay of feedback and cooling begins to define the morphology of early galaxies. As metals spread, cooling becomes more efficient at lower temperatures, allowing clouds to fragment into many smaller cores instead of collapsing into a single massive star. This change in fragmentation scale shifts the stellar initial mass function toward lower masses, creating stars capable of surviving for billions of years, the first long-lived witnesses to cosmic history. The lesser-known role of dust formed in the ejecta of the first supernova adds another layer. Even in tiny amounts, dust grains provide surfaces for molecular hydrogen to form more efficiently, further enhancing cooling in enriched regions. The first irony here is that the seeds of planetary systems are sown before there are even stable galaxies to host them. The second is that dust, often thought of as an obstruction to clear views in the modern universe, is in this era a catalyst for creation. The third is that enrichment proceeds fastest in the most clustered regions, meaning that the earliest chemically complex environments are also the most chaotic and short-lived. The uncertainty is how much of this dust survives the violent conditions of its birth. Some models suggest most is destroyed in shocks, while others find enough survives to influence subsequent cooling. The light from the first supernova is brief but intense, in some cases outshining entire early galaxies for weeks or months, though it cannot be seen across the neutral universe without absorption. Locally, it floods the surrounding gas with high-energy photons, contributing to the ionization and heating of the intergalactic medium. In regions where multiple supernovae occur within a short period, the cumulative effect can carve large hot cavities in the gas, merging with ionized bubbles from stellar radiation and accelerating the progress of reionization. Meanwhile, new stars continue to form in halos that avoided the most destructive effects, adding fresh ionizing sources to the growing network of luminous regions. The cycle of birth, life, death, and enrichment accelerates. The fact that drives this acceleration is that enriched gas cools more efficiently and collapses faster, meaning that the delay between the death of one generation and the birth of the next shortens with each step. The lesser-known detail is that in enriched halos, fragmentation can produce both low-mass, long-lived stars and still massive short-lived stars in the same cluster, a pattern that will persist into later cosmic epochs. The first irony is that the presence of metals, which allows smaller stars to form, does not eliminate the formation of massive stars entirely. Their intense feedback continues to shape the environment. The second is that halos that were too small to form stars before enrichment may now be able to, because the lowered cooling threshold brings them into the regime where gas collapse is possible. The third is that this democratization of star formation also increases competition for gas, as more halos can now draw material from the same filaments. The uncertainty in this stage lies in the balance between enrichment-driven acceleration and feedback-driven suppression. The net effect determines how quickly the universe transitions from a patchy mixture of light and dark to one in which reionization approaches completion. Beyond the enriched regions, population 3 star formation persists in isolated pockets, continuing to produce massive stars and occasional supernovae. These remnants, rare but luminous, contribute sporadically to the ionizing background, and their chemical signatures may be preserved in the atmospheres of low-mass stars formed in mixed environments. The overall structure of the universe now resembles a cosmic quilt, bright metal-rich regions stitched together by filaments of partially ionized gas, surrounded by vast stretches of untouched neutral hydrogen. The largest ionized bubbles begin to merge into structures tens of millions of light-years across, while the smallest remain confined to single halos. The growth of these regions is not uniform. It is shaped by the clustering of halos, the distribution of enriched gas, and the reach of high-energy photons from early black holes and X-ray binaries. The light from all these sources slowly raises the ionization fraction of the intergalactic medium, but complete reionization is still hundreds of millions of years away. The first irony of this transitional universe is that its most luminous events are also its most fleeting. The second is that the largest structures forming now, the earliest protogalaxies, are built from mergers of halos that individually could not sustain continuous star formation. The third is that the chemical and thermal state of the gas, rather than just its mass, increasingly determines which regions will host the next bursts of light. The quiet uncertainty is how evenly metals are spreading. The answer will decide how long truly pristine star formation can survive, and how quickly the population of long-lived stars begins to dominate. For now, the enriched regions glow faintly in the ultraviolet, the shadows between them remain deep, and the cosmic web tightens its threads, drawing matter into the nodes where the next chapters of light will be written. As enrichment spreads, the universe begins to shift toward a new mode of star formation. The earliest clusters of enriched halos grow through mergers, their combined mass deepening gravitational wells and allowing them to hold on to gas even under the pressure of photoheating from nearby ionizing sources. Within these larger halos, the gas is both chemically enriched and dynamically complex, threaded with turbulence from supernova shocks and accretion flows. The fact defining this stage is that these deeper potential wells mark the transition from small transient star-forming halos to the first-bound protogalaxies systems capable of sustaining multiple generations of star formation over extended periods. The lesser-known detail is that the gas in these halos is often funneled inward along the same cold filaments that fed the earliest mini-halos, but now those filaments can penetrate further before being shock-heated, delivering cool, enriched material directly to the galaxy's center and enabling rapid starburst episodes. The first irony is that the very feedback processes that expelled gas from smaller halos now help concentrate it in larger ones as outflows and shocks drive material into deeper wells where it can be captured again. The second is that while the overall metallicity of these early galaxies is extremely low by later standards, it is already high enough to produce stars across a full range of masses, ending the reign of exclusively massive population 3 stars in these environments. The third is that the gravitational assembly of these protogalaxies proceeds without any awareness of the luminous transformation it is enabling, driven purely by the silent equations of mass and motion. The quiet uncertainty here is in the exact star formation efficiency within these first galaxies. Simulations suggest a wide range depending on feedback strength, merger history, and gas accretion rates, and this efficiency directly impacts the timeline of reionization. Within the protogalaxies, star formation ignites in bursts. Clumps of enriched gas collapse under their own weight, fragmenting into stellar nurseries, where both massive and low-mass stars form side by side. The ultraviolet light from the massive stars begins to overlap in the surrounding medium, creating larger ionized regions that can extend beyond the galaxy's virial radius. Supernovae from these massive stars enrich the gas, further increase turbulence and drive galactic winds that can escape into the intergalactic medium. Some of this outflowing gas mixes with pristine material along the galaxy's outskirts, while some is lost entirely, seeding nearby filaments with metals and energy. The lesser-known role of these winds is that they can carry metals into low-density regions, where they would not otherwise arrive for hundreds of millions of years, subtly altering the cooling properties of distant halos yet to form stars. The first irony here is that galaxies in feeding themselves through cold flows are simultaneously feeding the rest of the universe through their winds. The second is that while their most massive stars may live for only a few million years, the metals they produce will persist in the cosmic medium for the rest of cosmic history. The third is that although these systems are the first true galaxies, they are far smaller and fainter than most galaxies that will exist later, and their light is still easily hidden by intervening neutral gas. The uncertainty concerns how effectively these outflows escape. In shallow potential wells, much of the enriched gas can be lost, but in deeper wells the gas may fall back, cycling through repeated bursts of star formation. In the space between these protogalaxies, the intergalactic medium is slowly changing. X-rays from early black holes, high-mass X-ray binaries, and possibly remnants of massive population threes. Dust stars penetrate the neutral gas over long distances, heating it more uniformly than ultraviolet light can. This heating raises the spin temperature of hydrogen, altering its 21 centimeter signal and changing the conditions for later reionization. In some regions, X-ray heating occurs before ultraviolet ionization, creating a layered history where the gas is warm but still neutral until nearby ionized fronts arrive. The fact here is that X-rays have a mean free path hundreds of times longer than ultraviolet photons in the neutral medium, allowing them to influence the temperature of gas far from any galaxy. The lesser-known consequence is that this preheating can suppress small-scale structure formation by increasing the thermal pressure in low-mass halos, further biasing star formation toward larger systems. The first irony is that black holes, the remnants of collapse, are now among the most influential sources of energy in shaping the future of the gas. The second is that these X-ray sources can aid reionization indirectly by making ionization fronts propagate more quickly through preheated gas. The third is that even a few such sources can dominate the heating of large cosmic volumes, creating an influence disproportionate to their numbers. The uncertainty remains whether this X-ray background was dominated by stellar remnants or by accretion onto more massive early black holes, seeded by direct collapse. As more protogalaxies form and grow, the topology of reionization changes. Isolated ionized bubbles begin to merge into extended networks, connected along the filaments of the cosmic web, where galaxy density is highest. The neutral regions shrink into irregular shapes, retreating into the interiors of large voids, and the densest clumps where recombination rates are high. The speed of this process depends strongly on the clustering of galaxies. In dense knots of the web, reionization proceeds quickly, while in sparsely populated regions it can lag by hundreds of millions of years. The lesser-known complexity is that even after an ionized region forms small neutral clumps known as Lyman limit systems, can survive within it, casting shadows and consuming ionizing photons, thereby regulating the overall progress. The first irony is that the most ionized regions are not perfectly transparent, but instead contain a labyrinth of absorbers that keep their own small darkness alive. The second is that these same absorbers may help maintain the pressure balance within the ionized medium, influencing its structure. The third is that such small-scale structures, though negligible in mass, compared to the rest of the gas, can control the photon budget for reionization. The uncertainty is how numerous and long-lived these clumps are in the early universe, and thus how much they delay the final stages of reionization. By this stage, the ultraviolet background has grown strong enough in many regions to affect gas cooling even in relatively large halos. The photoionization heating raises the gene's mass, preventing low-mass galaxies from forming stars unless they are exceptionally dense. This suppression ensures that reionization becomes increasingly driven by the larger galaxies forming in the deepest gravitational wells. The fact that emerges from this is that reionization is both a global and a highly selective process, global in its eventual coverage but selective in the environments where new light is produced. The lesser-known detail is that the suppression of small halos can lead to a temporary decline in the rate of new star formation, even as the ionized fraction continues to rise, creating a complex relationship between light production and the growth of reionization. The first irony is that the process of brightening the universe necessarily limits the number of new lights that can form. The second is that the regions where reionization finishes first may see a lull in star formation soon after, as their smallest contributors are shut down. The third is that this slowdown can make it appear from a distance in time that reionization was less efficient than it truly was. The uncertainty lies in whether the final push to full ionization comes from the continued growth of existing galaxies, or from a resurgence of activity in systems that temporarily fell below the cooling threshold. For now, the universe is in the midst of transformation. Proto-galaxies blaze in clustered hubs, their light spilling into the cosmic web. X-ray sources warm the shadows. Neutral pockets cling to their opacity in the voids. The balance tips steadily toward a luminous cosmos, though the last vestiges of the ancient darkness still hold on, awaiting the moment when the entire intergalactic medium will become transparent once more. The interconnected networks of ionized regions now stretch across tens of millions of light-years, linking clusters of proto-galaxies along the densest filaments of the cosmic web. Light from countless massive stars pours into the intergalactic medium, steadily eroding the neutral hydrogen that has dominated since the recombination era. The fact that anchors this stage is that the universe is well into the epoch of reionization, with perhaps half of the cosmic volume already ionized, though the process is far from complete. The large-scale structure of reionization reflects the underlying matter, distribution galaxy. Rich filaments form the first continuous corridors of ionization, while vast underdense voids remain dark until fronts from multiple directions converge upon them. A lesser-known detail of this phase is the presence of relic neutral hydrogen inside ionized regions trapped within self-shielded clumps that can survive for hundreds of millions of years. These pockets, often with column densities exceeding the Lyman limit, act as sinks for ionizing photons and require a steady supply of new radiation to maintain the surrounding ionization. The first irony is that the most luminous regions of the young universe are riddled with small shadows that persist in defiance of the surrounding brightness. The second is that the smallest structures can command the largest share of the photon budget, slowing the advance of light across the cosmos. The third is that the very processes that create these absorbers, gravitational collapse and cooling, are the same that drive star formation elsewhere. The quiet uncertainty here concerns the abundance and distribution of these systems, for their prevalence directly affects the timescale over which the final neutral reservoirs are erased. Within the largest ionized networks, star formation in protogalaxies continues in bursts. Gas accretion along cold filaments feeds the inner regions, replenishing fuel for stellar birth even in the face of strong feedback from supernovae and stellar winds. In the most massive systems, gravitational potential wells are deep enough to retain much of the outflowing gas, enabling cycles of enrichment and renewed star formation. These are the environments where the first stellar populations resembling those in later galaxies begin to dominate mixtures of massive short-lived stars and smaller long-lived ones, producing both intense ultraviolet radiation and a gradual build-up of older stellar mass. The lesser-known role of these early galactic environments is in shaping the emerging ultraviolet background. While isolated galaxies contribute locally, it is the clustered hubs that dominate the large-scale ionization fronts, because their overlapping spheres of influence extend far into the intergalactic medium. The first irony is that reionization on cosmic scales is effectively the work of a minority of galaxies in the densest neighborhoods. The second is that galaxies in lower density regions, though numerous, have their light absorbed close to home and rarely influence the global topology. The third is that some regions of space will finish reionization long before others, creating a time-lagged universe in which different volumes exist in different ionization states simultaneously. The uncertainty lies in how early massive black holes growing through accretion in these galaxies contribute to the ionizing budget. Observations suggest that active galactic nuclei are rare in this epoch, but their hard spectra could ionize helium and contribute to hydrogen reionization if present in sufficient numbers. Beyond the bright hubs, the ionization fronts advance unevenly into the voids. The density of hydrogen in these underdense regions is low, so relatively few photons are required to ionize them, but the isolation of these areas means that the fronts must travel long distances to reach them. Along the way, they encounter filaments and small clumps that absorb and scatter radiation, making the propagation of light an irregular process. The fact here is that the geometry of the cosmic web continues to dictate the speed of reionization. Fronts can advance quickly through channels of low density, but slow dramatically when forced across dense self-shielded structures. The lesser-known effect of this geometry is that voids may appear fully ionized, while the densest knots embedded within them remain neutral, a phenomenon that complicates the interpretation of observational data. The first irony is that the regions that seem easiest to ionize can still harbor hidden reservoirs of neutral gas. The second is that the same low density that allows rapid ionization also limits star formation, meaning these voids contribute little to the process that changes them. The third is that the final remnants of neutral hydrogen may not be in the deepest voids at all, but in high-density pockets that resisted ionization from the beginning. The uncertainty here lies in pinpointing the locations of these final reservoirs, as they determine where the last stages of reionization will unfold. In the galaxies themselves, chemical enrichment accelerates. Metals from multiple generations of stars accumulate in the interstellar medium, further enhancing cooling efficiency and enabling the formation of molecular clouds dense enough to birth smaller, longer-lived stars. Dust becomes more abundant, providing both shielding from ionizing radiation and surfaces for molecule formation. This changes the character of star formation in enriched environments. Gas can fragment into clusters of low-mass stars that will survive for billions of years, many of which may still exist in the modern universe as ancient stellar populations. The fact is that by this stage, truly pristine gas is rare in the star-forming regions of massive halos, though it may persist in isolated pockets far from any galaxy. The lesser-known point is that these enriched molecular clouds can coexist with ongoing bursts of massive star formation, leading to mixed-age stellar populations within the same galaxy. The first irony is that the stars most likely to survive to the present day form in the same places as those that burn out fastest. The second is that the most chemically complex environments are also the most hostile to the long-term stability of small galaxies, as intense feedback can strip them of gas. The third is that the metal content that enables planetary building blocks is already present in trace amounts billions of years before any planet forms. The uncertainty here concerns the fate of the smallest enriched systems. Some will merge into larger galaxies, while others may be destroyed by tidal interactions or feedback, leaving only their oldest stars as evidence. As reionization progresses, the ultraviolet background becomes increasingly uniform on large scales. Ionizing photons from distant galaxies can now travel significant fractions of the cosmic horizon without being absorbed, linking once isolated regions into a single ionized network. Yet at small scales, inhomogeneity persists. Filaments, clumps, and dense galaxy halos maintain structure in the radiation field, creating a mottled transition from the patchwork of earlier epochs to the smooth transparency of later times. The fact here is that the completion of reionization is as much about the decline of neutral clumps as it is about the growth of ionized regions. The lesser-known challenge is that recombination in high-density areas remains significant even late in the process, requiring a continuous photon supply to keep them ionized. The first irony is that the moment the universe becomes transparent again is also the moment it begins to require constant maintenance to stay that way. The second is that the same transparency that allows light to cross the cosmos also reveals its emptiness on the larger scales. The third is that while reionization transforms the universe's visual character, it is nearly invisible in its direct effects on the matter distribution. The uncertainty is in exactly when and how the ionized fraction approaches unity. The timeline may vary by hundreds of millions of years between the earliest and latest regions. By the close of this stage, the universe is a vast network of luminous galaxies embedded in an almost fully ionized medium, with only scattered remnants of neutral hydrogen persisting in protected niches. The Dark Ages are nearly gone, but the last holdouts remain waiting to be erased by the combined light of a cosmos that is finally almost entirely awake. The final neutral pockets of the intergalactic medium lie hidden within the folds of the cosmic web clinging to the shadows cast by dense clumps and self-shielded filaments. These are the last remnants of a state that once filled the universe, and their erasure will mark the end of the epoch of reionization. The fact that defines this stage is that the ionized fraction of the cosmos is now well above 90%, with only the most resistant regions still holding on to their hydrogen atoms. They survive because recombination rates in high-density environments outpace the arrival of ionizing photons demanding a sustained and concentrated radiation field to overcome their defenses. A lesser-known detail is that these neutral reservoirs are not randomly distributed. They tend to inhabit the inner cores of overdense regions where gravitational collapse has pulled gas into compact structures, as well as in certain filaments where geometric alignment with ionizing sources is poor. The first irony is that the most stubborn darkness persists not in the emptiest voids, but in the richest knots of matter. The second is that the same gravitational processes that gave rise to the galaxies driving reionization also created the sanctuaries that delay its completion. The third is that the end of the Dark Ages is slowed most by regions that have in some sense already participated in the cosmic transformation, their outskirts glowing while their cores remain opaque. The quiet uncertainty here is how long these last pockets survive before the growing ultraviolet background overwhelms them. The timescale may range from a few tens to 100 million years, depending on their density and proximity to powerful sources. In the bright regions that now span most of space galaxies continue to grow through mergers and steady accretion from the surrounding intergalactic medium. The largest protogalaxies of earlier epochs have now become small but recognizable galaxies, with organized stellar populations, nascent disks, and more chemically diverse interstellar media. Star formation continues in bursts fueled by inflows along filaments and by the recycling of gas expelled in earlier feedback episodes. The enriched gas allows for efficient cooling even in moderately dense regions, producing a wider range of stellar masses than in the first generations. The lesser-known role of these galaxies in the final phases of reionization is their maintenance of the ionized state. While the early stages of the process were driven by the rapid growth of ionized regions, the final stages depend on the continuous replacement of photons lost to recombination. The first irony is that finishing reionization requires as much effort to sustain as to initiate. The second is that the galaxies most responsible for holding the medium ionized are not necessarily the most massive or luminous, but rather those with steady ongoing star formation. The third is that even galaxies whose light cannot travel far contribute indirectly by ionizing their immediate surroundings, reducing the burden on the larger photon budget. The uncertainty in this stage lies in the relative contribution of faint, numerous galaxies versus rarer, brighter systems. Both play a role, but the balance determines the fine structure of the final reionization topology. Between the galaxies, the ultraviolet background has become nearly uniform at large scales, allowing ionization fronts to advance into even the most remote corners of the cosmic web. In some cases, the final neutral regions are breached from multiple directions at once, their hydrogen atoms stripped in a matter of tens of thousands of years an instant compared to the eons before. The fact here is that the mean free path of ionizing photons has increased dramatically, making the intergalactic medium transparent across cosmological distances. The lesser-known consequence is that this transparency allows ionizing photons to escape more easily from galaxies into the wider universe, creating a feedback loop that accelerates the final cleanup of neutral gas. The first irony is that the last stage of reionization is both the slowest in global terms and the fastest in local terms, with neutral regions vanishing abruptly once exposed. The second is that the galaxies erasing these final reservoirs often have no direct connection to them, their light arriving after a journey of millions of years. The third is that the moment the last neutral gas is gone, the same photons that destroyed it will travel unimpeded through vast empty spaces, their original purpose fulfilled, but their journey just beginning. The uncertainty concerns whether faint undetected populations of active galactic nuclei also contribute to this late phase. Their harder spectra could ionize both hydrogen and helium, potentially altering the thermal history of the medium. As reionization closes, the thermal state of the intergalactic medium changes. The influx of ionizing photons heats the gas to temperatures of 10 to 20,000 Kelvin, raising the sound speed and altering the future growth of structure on small scales. Low-mass halos find it increasingly difficult to accrete fresh gas, their potential wells too shallow to overcome the pressure of the heated medium. The fact is that this photoheating feedback permanently shifts the threshold for galaxy formation, biasing future growth toward larger halos. The lesser-known outcome is that some small galaxies that formed before reionization and managed to hold on to their gas can continue forming stars in isolation, surviving as fossil systems for billions of years. The first irony is that reionization, while enabling the transparency that reveals the universe, also suppresses the very processes that built the light sources in the first place. The second is that these fossils preserve chemical signatures of the earlier star formation long after the galaxies that reionize the cosmos have evolved beyond recognition. The third is that the process that connects all regions into one luminous universe simultaneously limits the diversity of small-scale structures that can form afterward. The uncertainty is how many of these fossils survive into the present epoch, as their detection could offer direct clues to the earliest phases of galaxy formation. By the final moments of reionization, the universe has been transformed from a patchwork of light and shadow into a nearly uniform bath of ionized hydrogen. Galaxies, once isolated beacons, now shine into an open sky, their light able to traverse cosmological distances without being scattered by intervening neutral gas. The cosmic microwave background still present and now cooled to just a few Kelvin passes, unimpeded through the intergalactic medium, its faint ripples overlaid with the imprint of the ionized universe. The fact that lingers at the close of this epoch is that the transparency we now take for granted was hard-won, the result of countless generations of stars and galaxies building a photon budget sufficient to reshape the entire cosmos. The lesser-known reality is that the ionized state is not permanent by nature. It must be maintained against recombination, and the photon production of later cosmic epochs will continue to play this role invisibly. The first irony is that the end of reionization is not an ending but the start of a new equilibrium. The second is that the galaxies that accomplish this transformation are in most cases too faint to be seen directly with current instruments. The third is that although the Dark Ages are gone, their legacy remains in the structure and chemistry of the gas and stars that emerged from them. The quiet uncertainty even here is in the precise redshift and duration of this transition. Though its broad contours are understood, the exact timing remains a subject of measurement and debate, pieced together from faint signals and indirect traces. With the last shadows erased, the universe enters the long middle act of its history, a time of continuous star formation, galaxy growth and gradual change. But the memory of its first light remains etched in every atom of metal, every ancient star and every photon still travelling outward from those first luminous sources. The end of reionization leaves behind a universe bathed in a nearly uniform ultraviolet background, its hydrogen fully ionized, and its helium mostly singly ionized, with only denser clumps retaining partial neutrality. In this transformed cosmos, the large-scale view is one of transparent filaments, knots and voids, all threaded by light from countless galaxies. The fact that shapes this stage is that the intergalactic medium is now optically thin to ionizing photons, meaning that light from one end of the cosmic web can in principle travel immense distances without being absorbed. This transparency connects distant galaxies into a shared radiative environment, altering how they evolve and interact with their surroundings. A lesser-known detail is that the ultraviolet background itself is not perfectly smooth. Fluctuations arise from the clustered distribution of galaxies and from residual absorbers that filter the light in complex ways, producing subtle variations in the ionization rate across different regions. The first irony is that the universe's new openness still carries the imprint of the very structures that made it possible. The second is that these fluctuations invisible to the eye shape the conditions for star formation, in ways that will echo for billions of years. The third is that even after reionization, the cosmic web retains shadows of its earlier opacity in the form of Lyman limit systems and damped Lyman alpha absorbers that persist in galaxy halos. The quiet uncertainty concerns how long these residual absorbers continue to regulate the transmission of light, and whether they influence the thermal evolution of the intergalactic medium in measurable ways. In the galaxies themselves, star formation enters a new regime. The gas is enriched, the cooling times are short, and the fragmentation scale has shifted toward the formation of numerous lower-mass stars alongside the still-present massive ones. This change alters the stellar initial mass function, producing long-lived stars in significant numbers for the first time. Many of these will survive to the present day, carrying in their atmospheres the chemical record of the universe's first billion years. The fact here is that the metals forged in the first and second generations of stars are now cycling through multiple rounds of star formation, creating increasingly complex chemical mixtures. The lesser-known role of dust becomes more pronounced in this stage. In enriched galaxies, dust grains shield molecular clouds from the pervasive ultraviolet background, allowing molecules to survive and enhancing the efficiency of cooling and collapse. The first irony is that the very radiation that filled the cosmos to end the Dark Ages must now be blocked in small volumes to allow star formation to proceed efficiently. The second is that dust, which can obscure light in later cosmic history, is here a catalyst for new light. The third is that without the ultraviolet background, the cooling and fragmentation that create diverse stellar populations would be far more chaotic, yet the background also suppresses star formation in the smallest galaxies. The uncertainty remains in how the balance between suppression and regulation plays out in different environments. The answer will influence the growth rates of galaxies across the early universe. With the transparency of the intergalactic medium established, the light from young galaxies travels unimpeded to fill the cosmic horizon, but it is joined by another emerging signal, the ionization of helium. While hydrogen ionization is largely complete, helium requires higher energy photons to remove both its electrons. The fact is that this second ionization of helium, often called reionization, begins later and is thought to be driven primarily by the harder spectra of quasars and active galactic nuclei that appear as massive black holes grow in galaxy centers. A lesser-known aspect is that the partial ionization of helium left from earlier stages means that this process does not begin from scratch. Rather, it intensifies in regions where hard photons become abundant, leading to localized heating of the intergalactic medium. The first irony is that the universe is already transparent to most radiation, yet this second ionization reshapes its thermal state significantly. The second is that helium, a minority component by mass, can control the large-scale temperature evolution of the medium for hundreds of millions of years. The third is that the same black holes that once may have slowed early star formation through feedback now become agents of large-scale heating. The uncertainty concerns the precise timing and duration of this phase, as direct observations at the relevant redshifts are challenging. On the scale of the cosmic web, matter continues to flow along filaments into galaxy clusters and groups, deepening gravitational wells and triggering mergers. These mergers are not only structural events but also catalysts for intense starbursts and the growth of central black holes. The fact is that the rate of mergers in this early post-reionization universe is high, and the gravitational energy released during these interactions drives shocks and turbulence that further mix metals into the surrounding medium. The lesser-known effect is that these turbulent flows can carry metals far beyond the galaxies themselves, enriching the circumgalactic and intergalactic medium to levels that will remain measurable for billions of years. The first irony is that the boundaries of galaxies blur as their material is exchanged with the larger cosmic environment. The second is that the same processes that grow galaxies also strip them of some of their gas-setting limits on their future growth. The third is that the most massive galaxies of this time which dominate their regions are still dwarfed in mass and scale by the giants that will form later. The uncertainty lies in how these early mergers set the stage for the morphology of galaxies seen in the more mature universe. In the background of all this activity, the 21-centimeter signal of neutral hydrogen shifts into a new role. With the global ionization of hydrogen, the signal now primarily traces residual neutral gas in galaxy halos and dense intergalactic clumps. The fact is that these absorbers produce a forest of lines when seen against bright background sources like quasars known as the Lyman alpha forest, which becomes a key probe of the distribution and state of the intergalactic medium. The lesser-known connection is that the statistics of this forest preserve information not only about density fluctuations, but also about the temperature and ionization history of the medium, making it a record of both cosmology and astrophysics. The first irony is that the same absorption features that reveal the large-scale structure also obscure the light of the background source. The second is that the forest thins as the universe expands, yet even its fading traces remain one of the richest archives of the early universe. The third is that by studying these small-scale shadows, one can infer the state of volumes of space far larger than the shadows themselves. The uncertainty is in how much of the fine detail in the forest reflects the immediate environment of galaxies versus the broader conditions of the intergalactic medium. By the close of this stage, the universe is in a state of comparative stability compared to the turbulent transitions of the Dark Ages and reionization. The ultraviolet background is strong and pervasive galaxies are growing and enriching their surroundings, and large-scale structure is well defined. Yet beneath this stability lies continuous change. Stars are being born and dying. Black holes are growing and shining, and gas is flowing along the cosmic web to fuel the next phases of galactic evolution. The transparency achieved after reionization is not merely an observational convenience. It is a physical state that alters the trajectory of cosmic history, setting the stage for the gradual long-term transformation of the universe into the one we recognize in its later epochs. The ultraviolet background, now well established, threads the universe with a steady field of ionizing light that reaches into the halos of galaxies and the spaces between them, holding hydrogen in its ionized state and keeping the intergalactic medium transparent. The fact that anchors this stage is that this pervasive radiation field is sustained by the combined output of billions of massive stars and a smaller but significant contribution from quasars, each source adding its photons to a pool that spans the observable cosmos. A lesser-known detail is that this background is not static. It fluctuates on timescales of tens to hundreds of millions of years, as populations of galaxies brighten and fade, as quasar activity rises and falls, and as mergers alter the star formation rates of entire regions. The first irony is that the stability of the ionized state depends on an inherently dynamic set of contributors. The second is that the galaxies that now maintain cosmic transparency are often far less extreme than the luminous giants of the reionization era, yet their steady production is more important over the long term. The third is that this background, though invisible to human eyes, defines the boundaries of where and how new stars can form. The quiet uncertainty concerns how uniform the background truly is, for small variations could subtly bias the evolution of galaxies in ways not yet fully measured. Within galaxies, star formation has settled into more diverse patterns. The most massive systems are building extended stellar populations with a mixture of ages, their interstellar media enriched by successive generations of supernovae. The fact is that metallicities in these galaxies now exceed 1,000th of the solar value in many regions, a threshold that dramatically enhances cooling efficiency and allows the formation of low-mass stars in abundance. The lesser-known role of stellar winds becomes increasingly important in regulating this process. Winds from evolved stars return enriched material to the interstellar medium, contributing to the cycling of gas without the violence of supernovae. The first irony is that winds which might seem gentle compared to explosions can be as influential in sustaining star formation by feeding fresh material into molecular clouds. The second is that much of the mass returned by dying stars is in elements heavier than helium, ensuring that the chemical diversity of galaxies continues to grow. The third is that these same winds on larger scales can contribute to the diffuse enrichment of the circumgalactic medium. The uncertainty lies in how much of this returned gas is retained versus lost to galactic outflows in lower mass systems. The growth of structure at this time is dominated by mergers along the cosmic web. Small galaxies are drawn into larger ones, and groups of galaxies coalesce into early clusters. The fact here is that the gravitational potentials of these clusters are deep enough to trap enormous volumes of hot ionized gas in their intracluster media, which can remain at temperatures of millions of Kelvin for billions of years. The lesser-known point is that this hot gas, while too diffuse to form stars, plays a key role in galaxy evolution, by exerting ram pressure on incoming galaxies, stripping their gas and altering their star formation histories. The first irony is that the densest, most massive environments in the universe can be the least hospitable to star formation. The second is that clusters which appear as concentrations of light are also vast reservoirs of darkness in terms of cold gas content. The third is that the same gravity that assembles these systems ensures that their constituent galaxies are constantly reshaped through interactions. The uncertainty is in how early these intracluster media become chemically enriched for their composition, records the integrated history of all past star formation within the cluster. On the intergalactic scale, the filaments of the cosmic web continue to serve as the main channels for gas accretion onto galaxies. Cold flows penetrate deep into halos, especially at high redshifts, delivering fresh material for star formation. The fact is that these flows are narrow and coherent, allowing galaxies to maintain star formation even in the presence of strong feedback. The lesser-known consequence is that the geometry of these inflows can imprint angular momentum on galaxies, influencing their eventual rotation curves and morphologies. The first irony is that the large-scale arrangement of matter determines the spin of systems billions of times smaller. The second is that these filaments are themselves shaped by the earliest density fluctuations from the universe's first moments, meaning the rotation of a galaxy is linked to patterns set before any stars existed. The third is that the same flows that feed galaxies can also carry metals outward, if winds are aligned with them, turning the channels into two-way conduits. The uncertainty here lies in the degree to which these flows persist, as the universe ages and feedback processes strengthen. In the halos of galaxies, the circumgalactic medium becomes increasingly complex. This diffuse multi-phase gas reservoir contains both hot ionized material from feedback and cooler, denser clouds that may eventually fall into the galaxy to fuel new star formation. The fact is that the circumgalactic medium holds a substantial fraction of a galaxy's baryonic mass, often exceeding the mass of gas in its interstellar medium. The lesser-known detail is that much of the metal content of galaxies resides here, locked in tenuous clouds that are difficult to detect directly, but can be revealed through absorption lines in the spectra of background quasars. The first irony is that a galaxy's chemical richness may be most fully expressed outside the region where its stars reside. The second is that this reservoir is both a product of and a prerequisite for continued star formation. The third is that the balance between inflow and outflow in this region can determine the long-term fate of the galaxy more decisively than the processes within its disk. The uncertainty is in the lifetime of these cool clouds within the hotter halo environment. Their survival dictates how effectively galaxies can recycle expelled material. Meanwhile, the intergalactic medium itself cools slowly from the heating of reionization, its temperature declining as the universe expands through localized heating events from quasars and structure formation shocks punctuate this gradual trend. The fact here is that the thermal history of this medium is a record of both large-scale astrophysical events and the slow march of cosmic time. The lesser-known implication is that the cooling rate influences the detectability of the intergalactic medium in various wavelengths, from the far ultraviolet to the X-ray. The first irony is that while the medium is nearly invisible, its physical state affects the visibility of everything else. The second is that its smoothness on large scales hides the small-scale density fluctuations that shape galaxy evolution. The third is that the energy content of this diffuse component rivals or exceeds that locked-in all-stars combined. The uncertainty lies in the extent to which non-gravitational heating processes from early black holes or cosmic rays have left lasting imprints on its temperature. By the close of this stage, the universe is well into its post-reionization maturity. Galaxies are numerous, chemically varied and structurally diverse, the cosmic web is sharply defined, and the background radiation fields are stable enough to maintain the ionized state of hydrogen across cosmic distances. Yet the seeds of future change are everywhere. Mergers will continue to transform. Galaxies, quasars will flare and fade, and the slow enrichment of the universe will lay the groundwork for complex structures, including planetary systems billions of years later. The cosmic night that once followed recombination is now an unbroken expanse of light, and the first stars that began this transformation have been gone for billions of years, their legacy written into every atom heavier than helium and every photon that still drifts through the infinite openness they helped create. With the universe fully transparent to ultraviolet light, and the large-scale structure well defined, the growth of galaxies becomes the dominant sculptor of the cosmic landscape. The fact that defines this stage is that galaxy formation is now regulated less by the global processes that ended the Dark Ages, and more by local environments, merger histories, and the balance between gas accretion and feedback. Regions of high galaxy density evolve quickly, their members enriched and massive, while galaxies in lower density regions grow more slowly and may remain relatively pristine for longer. A lesser-known detail is that these environmental differences begin to produce the first clear morphological diversity, compact spheroidal systems in dense clusters, where mergers are frequent, and more extended disk systems in quieter regions where gas accretion is steady and undisturbed. The first irony is that the densest regions, rich in material and gravitational pull, are also the places where star formation can be quenched earliest by environmental processes. The second is that isolation, which limits access to resources, can preserve star-forming galaxies long after their clustered counterparts have gone dormant. The third is that the shape and internal motion of a galaxy may be determined as much by its neighborhood as by its own mass. The quiet uncertainty is how early these morphological distinctions become locked in, and whether later interactions can reverse them. Inside galaxies, star formation has shifted to a more continuous rhythm in many systems, supported by stable inflows along the filaments of the cosmic web. The fact here is that most of the stars forming now are low mass, and will live for billions of years, gradually building up the stellar mass that will dominate the universe in later epochs. The lesser-known role of giant molecular clouds is increasingly important. These dense, cold regions of gas are where nearly all star formation occurs, shielded from the ultraviolet background by dust and self-gravity. The first irony is that galaxies filled with billions of stars still depend on fragile small-scale clouds for their renewal. The second is that the conditions that allow such clouds to form are more likely in galaxies with enough metals to cool efficiently, meaning that the earliest chemical enrichment still dictates present-day star formation rates. The third is that while these clouds are the engines of stellar birth, their existence is temporary, often disrupted within tens of millions of years by the very stars they create. The uncertainty lies in how long galaxies can sustain these molecular reservoirs without exhausting or expelling their gas. On larger scales, the cosmic web continues to feed galaxies through narrow filaments that carry cold gas deep into halos. The fact is that these cold streams can penetrate even massive halos that have shock-heated outer atmospheres, delivering material to the inner regions where it can fuel new stars. The lesser-known complexity is that these inflows are not uniform. They can carry both pristine gas and gas already enriched by earlier generations of stars mixing at different rates, depending on turbulence and galaxy dynamics. The first irony is that the same channels that bring new fuel for star formation can also carry the chemical fingerprints of distant galaxies. The second is that inflows can maintain the rotation of galactic disks, even as mergers try to disrupt them. The third is that the stability of these flows depends on a delicate balance between the galaxy's gravitational potential, the density of the inflow, and the energy injected by feedback. The uncertainty is how long cold flows can dominate gas supply before heating and structural changes shift galaxies toward more internal recycling of gas. In the circumgalactic medium, the interplay between inflow and outflow grows more intricate. The fact here is that the hot, diffuse halo gas can confine cooler clouds and streams, allowing some of the outflowing material from supernovae and stellar winds to return as part of a galactic fountain cycle. The lesser-known role of magnetic fields becomes more visible here. Though weak compared to gravitational and thermal forces, they can influence the shape and survival time of cold clouds moving through hot gas. The first irony is that gas expelled in feedback seemingly lost to the galaxy can become its future fuel. The second is that the slow circulation of baryons through the circumgalactic medium means that some atoms may take billions of years to complete a single loop from galaxy to halo and back again. The third is that the amount of mass locked in this halo reservoir can exceed that of the stars inside the galaxy itself. The uncertainty is in the precise rates of exchange between these phases, which determines how star formation will evolve in the long term. Quasars and active galactic nuclei powered by accretion onto massive black holes flare intermittently across the cosmos. The fact is that their energetic radiation and outflows can heat and ionize gas far beyond their host galaxies, regulating both local star formation and the thermal state of the surrounding intergalactic medium. The lesser-known aspect is that many of these outflows are not spherical, but collimated into jets delivering energy along narrow paths that can trigger or suppress star formation depending on where they strike. The first irony is that the most concentrated sources of light can have the widest reaching influence through non-radiative energy injection. The second is that the same black holes once seeded in the deaths of the first stars now govern the evolution of entire galaxy clusters. The third is that their activity cycles, driven by gas availability, can create periods of quiescence in galaxies that would otherwise continue forming stars. The uncertainty is in how much these early active phases precondition the gas for the later reionization of helium which still lies in the cosmic future. In the intergalactic medium, the temperature has begun a slow decline after the heating from reionization, though regions affected by quasars remain warmer for longer. The fact here is that the expansion of the universe continues to thin this diffuse gas, lowering its density and reducing the overall recombination rate. The lesser-known point is that the ionization balance is still dynamic. While hydrogen remains fully ionized, small fluctuations in the ultraviolet background can cause measurable changes in the neutral fraction on large scales. The first irony is that the intergalactic medium, though nearly empty, still dominates the volume of the universe, and therefore the background against which all galaxies evolve. The second is that its subtle fluctuations can have disproportionate effects on the detectability of distant sources. The third is that the physics governing its state is simple in principle, yet challenging to measure directly in practice. The uncertainty is how long the temperature memory of reionization persists before it is erased by expansion, cooling, and new heating events. By the close of this stage, the universe is a fully connected network of galaxies, clusters and filaments, its hydrogen kept ionized by a balance between photon production and recombination losses. The cosmic web is sharper in contrast than ever before, with matter and light tracing the same vast scaffolding. Star formation continues in most galaxies, mergers reshape structures, and chemical enrichment advances in steady increments. The darkness that once dominated is now only a memory preserved in the spectra of ancient stars, and in the faint signals that astronomers will someday extract from the background radiation. The cosmos is luminous, dynamic, and already carrying within it the seeds of its distant future. The gradual slowing of star formation, the fading of quasars, and the quiet transition toward a more quiescent state billions of years ahead. The galaxies that now inhabit the cosmic web are more massive and chemically enriched than those of the reionization era, yet their growth still depends on the same fundamental processes of gas inflow star formation and feedback that have shaped them from the beginning. The fact that defines this stage is that star formation across the universe is nearing its historical peak, a crest in the long curve that began with the first stars and will eventually decline into the quiet future. In dense clusters and along the busiest filaments, mergers are frequent driving intense starbursts that can briefly double a galaxy's stellar mass in just a few 100 million years. A lesser-known detail is that these bursts are often short-lived, curtailed by the rapid consumption of available gas, and by the feedback from supernovae and active galactic nuclei which can heat or expel the remaining fuel. The first irony is that the periods of greatest brilliance in a galaxy's history often mark the beginning of its decline. The second is that while these bursts are visually and energetically dominant, the bulk of the universe's star formation at this time still occurs in more modest, steady environments. The third is that the chemical enrichment from even brief starbursts can alter the cooling and star formation patterns for billions of years afterward. The quiet uncertainty here is how evenly the star formation peak occurs across different environments. Cosmic averages hide the variations between the rapid evolution of clusters and the slower growth in the quietest voids. Inside galaxies, giant molecular clouds continue to be the primary sites of star formation, their dust-shielded interiors collapsing into clusters of newborn stars. The fact is that the stellar initial mass function now resembles the one familiar from later epochs, with a broad distribution that includes many low-mass stars destined to outlive the galaxies that birthed them. The lesser-known role of magnetic fields and turbulence in these clouds is critical. They can delay or accelerate collapse, influence the size of resulting stellar clusters, and help determine the fraction of gas converted into stars. The first irony is that the fate of galactic-scale star formation can hinge on processes happening within clouds only a few dozen light-years across. The second is that turbulence, often thought of as disorder, can provide the stability needed to form stars at a controlled pace. The third is that magnetic fields invisible and intangible to most measures can leave lasting imprints on the structure of stellar nurseries. The uncertainty lies in how the balance between turbulence, gravity, and magnetic support varies across environments of different metallicity and radiation backgrounds. On the scale of galaxy clusters, gravitational assembly continues. The fact here is that clusters are already massive enough to trap hot X-ray emitting intra-cluster gas, which contains much of the baryonic matter within their volume. This hot medium, enriched by the outflows from generations of galaxies, can remain gravitationally bound for billions of years. The lesser-known detail is that the metallicity of the intracluster medium preserves a cumulative record of every supernova and galactic wind that has ever contributed to it, making it a fossil archive of chemical history on the larger scales. The first irony is that clusters which gather the most galaxies are also efficient at quenching their star formation by stripping away the very gas needed to make new stars. The second is that the hot gas filling their interiors is chemically richer than much of the intergalactic medium, yet too diffuse to cool and form stars directly. The third is that the same gravity that builds clusters also locks away baryons in a state that is inert for the purposes of star formation. The uncertainty is in the fraction of metals that escape from galaxies into this reservoir versus those that remain bound in stars or the circumgalactic medium. Along the filaments of the cosmic web, gas inflow remains an essential driver of galaxy growth. The fact is that these flows have narrowed with time as the surrounding intergalactic medium has been depleted by earlier accretion, making them more like discrete rivers than broad streams. The lesser-known effect of these narrow flows is that they can create asymmetric feeding patterns in galaxies, influencing spiral arm development and triggering off-center star formation. The first irony is that the large-scale geometry of the cosmic web can shape the fine details of a galaxy's morphology. The second is that galaxies on the same filament may share similar growth histories, even if they never merge, linked by the properties of their common supply channel. The third is that when a filament feeding a galaxy is disrupted by a merger or heating event, the impact can be as dramatic as removing a river from a fertile valley. The uncertainty lies in how stable these flows remain, as feedback processes become stronger and galaxies more massive. Active galactic nuclei continue to play a decisive role in this stage. The fact here is that the most massive black holes are now capable of producing outflows powerful enough to clear large fractions of gas from their host galaxies, either halting star formation entirely or regulating it to a low steady rate. The lesser-known aspect is that these outflows are often anisotropic, leaving some directions open to continued inflow and star formation, while sterilizing others. The first irony is that a process often described as feedback can both suppress and promote star formation depending on its geometry. The second is that black holes, the smallest central structures by scale in galaxies, can govern the fate of billions of stars. The third is that the seeds of these massive objects may trace back to a few rare collapses in the first 100 million years of cosmic history. The uncertainty remains in the precise duty cycle of active galactic nuclei at this epoch, as their influence depends on both their intensity and frequency. In the intergalactic medium, helium reionization begins to accelerate. The fact is that the harder photons required for double ionization of helium are now being produced in sufficient quantities by quasars to transform the thermal state of large volumes. This process heats the intergalactic medium to temperatures significantly above those reached during hydrogen reionization, altering pressure support in low-density regions. A lesser-known consequence is that this heating can erase small-scale density fluctuations in the intergalactic medium, subtly changing the fine structure of the Lyman alpha forest in quasar spectra. The first irony is that helium, the quiet second component of the baryonic mass, can so strongly affect the thermal balance of the universe. The second is that the same sources that drive this process, quasars, are rare and transient on the scale of cosmic time. The third is that helium reionization, though dramatic in its heating, is largely invisible except through indirect spectral signatures. The uncertainty is in the duration of this process. Whether it completes rapidly or over extended periods depends on the abundance and distribution of hard spectrum sources. By the close of this stage, the universe is vibrant with star formation, active black holes, and the steady assembly of structure on all scales. The peak of stellar birth rates is imminent, and the balance between inflow and feedback is at its most finely tuned. The hydrogen in the intergalactic medium remains fully ionized. Helium is entering its final transformation, and metals are steadily building up in every galactic and intergalactic reservoir. The cosmos, luminous and chemically evolving, is far removed from the simple cold darkness that followed recombination. Yet its vast web still holds the same underlying pattern, imprinted at the beginning, now lit and enriched, yet fundamentally the same scaffold on which the first stars ignited. The cosmic star formation rate reaches its peak, a crest in the long history of light production that began with the first stars. Across the universe, galaxies of all sizes are actively converting gas into stars, fueled by a combination of cold flows from the intergalactic medium mergers that compress gas into starburst regions, and the recycling of enriched material from earlier generations. The fact that defines this stage is that the rate of star formation per unit volume will never again be higher, even though the universe is already more than 2 billion years old. A lesser-known detail is that the peak is not uniform in time or space. Dense clusters reach their maximum earlier than galaxies in isolation, and low-mass galaxies often continue to increase their star formation for hundreds of millions of years beyond the cosmic average. The first irony is that the moment of greatest abundance in starbirth also marks the start of an irreversible decline. The second is that galaxies at this peak are creating stars that will outlive the era of peak activity by billions of years, carrying forward the chemical record of this time. The third is that the metals produced now will circulate through cosmic structures long after most of the galaxies responsible have changed beyond recognition. The quiet uncertainty is in how much of this peak is sustained by steady accretion versus short-lived bursts, a balance that affects the survival of gas reservoirs. Inside galaxies, the interplay between inflow star formation and feedback is at its most intense. The fact here is that feedback from supernovae and active galactic nuclei is both regulating and limiting star formation, preventing the complete exhaustion of gas in a single burst. The lesser-known role of stellar winds from massive stars is especially significant at this stage. They inject momentum and heat into surrounding gas before the stars end their lives, dispersing molecular clouds and shaping the next wave of star formation. The first irony is that the most productive stellar nurseries are dismantled by the very stars they create. The second is that this destruction is necessary to prevent galaxies from burning through their gas too quickly. The third is that while feedback limits immediate star formation, it can extend a galaxy's active lifetime by maintaining a supply of reaccreting material. The uncertainty is in how precisely the timing of feedback events aligns with the cooling times of surrounding gas, a relationship that determines whether the net effect is suppression or stimulation of further star formation. The cosmic web remains the primary infrastructure for galaxy feeding. The fact is that cold streams still deliver significant amounts of gas into massive halos, even as shock heating becomes more common in the most massive systems. The lesser-known point is that these streams can be clumpy, carrying small galaxies and enriched gas that mix into their hosts upon arrival, adding both fuel and diversity to their stellar populations. The first irony is that even as the largest galaxies become hot enough to impede fresh inflow, they still receive hidden channels of cool gas that preserve their star formation. The second is that the clumps within these flows can both feed star formation and serve as seeds for new satellite galaxies. The third is that the arrival of such material can trigger localized starbursts producing bright but short-lived enhancements in otherwise stable systems. The uncertainty lies in how these flows evolve as helium reionization progresses and the thermal state of the intergalactic medium changes. In the circumgalactic medium, the baryon cycle is fully active. The fact is that a galaxy's halo now acts as both a buffer and a reservoir, catching gas driven out by feedback and returning it over timescales of hundreds of millions of years. The lesser-known consequence is that this cycling can lead to a persistent exchange of metals between the galaxy and its halo, gradually enriching the circumgalactic medium to levels comparable to the interstellar medium in low metallicity systems. The first irony is that the majority of metals a galaxy produces may spend much of their time outside the galaxy. The second is that this enriched halo gas, though diffuse, can influence the cooling and stability of future inflows. The third is that the circumgalactic medium is in constant motion, yet from a cosmological distance it appears as a static envelope. The uncertainty is in how this circulation varies between actively star-forming galaxies and those entering quiescence. In galaxy clusters, the balance between inflow and quenching is sharply defined. The fact here is that the dense intracluster medium strips gas from incoming galaxies through ram pressure, rapidly shutting down their star formation, unless they are massive enough to resist. The lesser-known point is that some galaxies can retain small reservoirs of molecular gas shielded in their centers, sustaining low-level star formation even after their outer gas has been removed. The first irony is that the richest environments for galaxy assembly are often the most hostile to ongoing star formation. The second is that the same processes that quench galaxies and clusters can enrich the intracluster medium with metals and dust. The third is that the hot plasma filling the cluster's volume is both a product of past feedback and a barrier to future inflow. The uncertainty is in the timescales over which galaxies adapt to their new environments once captured by the cluster. Across the intergalactic medium, helium reionization continues driven by the hard spectra of quasars. The fact is that this process heats low-density gas to temperatures above 20,000 Kelvin, increasing the gene's mass and suppressing the collapse of small-scale structures. The lesser-known implication is that this heating can reduce the faint end of the galaxy luminosity function by preventing the smallest halos from forming stars at all. The first irony is that an event invisible to the naked eye can reshape the demographics of galaxies across the entire universe. The second is that helium reionization, though secondary in prominence to hydrogen reionization, has a larger impact on the thermal history of the universe during this period. The third is that the sources responsible are rare, yet their influence reaches across cosmic volumes. The uncertainty is in how uniformly this heating occurs, as patchy helium reionization could create temperature contrasts that persist for hundreds of millions of years. By the end of this stage, the universe is in full bloom. Star formation rates are at their highest, chemical enrichment is accelerating, and galaxies are assembling into the structures that will define their later evolution. The hydrogen in the intergalactic medium remains ionized. Helium is approaching full reionization, and the large-scale cosmic web continues to funnel material into galaxies of every size. The darkness that followed the Big Bang is now entirely gone, replaced by a cosmos filled with starlight-enriched gas and the energetic activity of black holes. Yet this moment of brilliance will not last indefinitely. From this peak, the slow decline will begin, shaped by the depletion of cold gas, the efficiency of feedback, and the expansion of the universe itself. The first stars that lit the darkness are long gone, but their descendants fill the sky, and the scaffolding laid down in the first few 100 million years now carries the full weight of a mature, luminous universe. The crest of star formation begins its slow descent, but the light it has created continues to travel outward, filling every corner of the transparent cosmos. Galaxies keep their quiet rhythms, some still merging in luminous bursts, others settling into steadier patterns, while the hydrogen between them remains ionized, a vast and open expanse. The helium that once held back the highest energy photons is nearly all doubly ionized now, its transformation complete, and the intergalactic medium cools slowly under the gentle influence of expansion. Cold gas still flows along the filaments of the cosmic web, but more of it now lingers in the halos of galaxies, part of the long cycle between inflow and feedback that will stretch on for billions of years. Metal atoms born in the cores of stars drift far beyond the places where they formed, mixing into the circumgalactic medium, the intergalactic medium, and even the hot reservoirs within clusters. They become traces of past creation, invisible, except when they catch the light of distant sources, but essential to the chemistry of all that will follow. The large-scale structure of the universe changes little to the eye filaments. Clusters and voids keep their shape, but the contents within them evolve in quiet ways. Star formation declines slowly, black holes accrete in fewer but still brilliant episodes, and the ultraviolet background remains steady enough to hold the intergalactic medium in its ionized state. From here, the changes will be gradual. The cosmos will keep its openness. Its galaxies will turn more of their gas into stars, and the threads of the web will continue to guide matter into dense knots. But the age of first light of patchwork, ionized bubbles growing and merging of the first metals, and the first long-lived stars is long past. What remains is the soft glow of a mature universe lit by the descendants of the first stars, their photons crossing immense distances without interruption, carrying the memory of that early transformation into every epoch that follows.